Hi students. Today we are learning the class 12 physics atom, chapter atom, and this one is the third video. This video is regarding the atomic spectra. Okay, so this is the atomic spectra is the thing which Rutherford cannot be explained in his nucleus model of atom. So this atomic spectra is explained by the Bohr. Understood now? So we will study today what is atomic spectra and different of spectrums like Lyman series. Then we will study about the Balmer series. Then we will study about the Paschen series. Then we will study about the Brackett series. Everything, all these series we will do study. Then we will do some question papers for the JE and NEET. So that will be there. So first we will study what is an atomic spectra. You know what is the difference between spectra and spectrum? We will just see. What is a spectra? Spectra. And what is spectrum? Very simple. This is plural. This is singular. This is man, singular. Plural, men. Same like spectra. Atomic, so many spectra is explaining about one atom, one spectra is there. Hydrogen atom, there is a spectra. Helium atom, there is another spectrum. Different atom, there is different spectrum. That is called as atomic spectra. Everybody clear now what is a spectra and what is a spectrum? It is a single spectrum is called a spectrum. Different spectrum is called spectra. So we will study what is a spectrum and different we will study about that one. Before that one, we will just go for the spectrum. We are studying about a spectrum which is visible and it is a continuous spectrum. Okay, we'll just read this one. Okay, so this is a white light source, white light. This is a prism. This one is a screen. And this one is an observation camera. So this full thing we called a spectrometer. Spectrometer. There will not be any white source here. This one is called spectrometer. Everybody clear now what is a spectrometer? So spectrometer, there will be a prism will be there. There will be a screen will be there. There will be a camera. I'll just remove what is a spectrometer. We will explain, we need this spectrometer afterwards. That's why I just explained this one here now. Okay. Yeah. Now, what is the medium here? Here it is air. The medium is air now. This white light is passing from air to prism. Prism is what is the medium? It is glass. If a white light is passing from one medium to another medium, it can be glass, it can be water. So that's why you see the spectrum in the just like a glass is also okay, the water is also okay. You can see this spectrum. If it is passing the white light from one medium to another medium, then this will separate into a spectrum. It is called continuous spectrum. We will just see what all the continuous spectrum. Violet, violet, indigo, blue, green, yellow, orange, red. These are the visible lights. Violet, indigo, blue, green, yellow, orange, red. So this lights, it is passing through like a wave. It is going like that. So this one, this wave lights, it is measured in the wavelength. It is called as nanometer. We can say wavelength. It is normally denoted in the name lambda. Lambda. So we'll just see what is the wavelength. Okay, wavelength is this light is passing through like a wave. Now you see the wave is like this. It is passing through, it is passing through, it is passing through. This one is the violet. Another wave is passing, so it is passing. So this one is called crust. This one is called crust. So if you draw a line from one crust to another crust, this one is called wavelength. Wavelength. Clear, no? This one is wavelength. Normally, wavelength is measured in the nanometer. Nanometers. Nanometers. I will just write it nanometers. Nano. Clear, no? Nanometer. So 1 nanometer is 10 raised to minus 9 meter is equal to 1 nanometer. 10 raised to minus 9 meter is 1 nanometer. Now everybody clear what is the wavelength? How the light is passing through? It is in the wavelength. It is from the crust to crust or even tuff to tuff also. From here to here also possible. That is called as tuff. T-O-U-G-H. Tuff. Tuff. So from here another tuff is coming. You see here. So from here this is also same. This is same as this one. This one is same. This one is same. Same, both are the wavelength. Clear, no? This one is the wavelength. So now we'll go for the continuous spectrum. Violet, indigo, blue, green, yellow, orange and red. These 7 colors is only basic color, but the spectrum is like a continuous one. So we will just see, these are the visible range of spectrum. We will just see the nanometer range. This one is from the 350 nanometer to 700 nanometers. So visible spectrum is from the 350 nanometer to 700 nanometers. Okay, so there will be 350.001. So there will be 350.002. It will go like this. So it will be 699.99. So it is a light will be continuously violet, indigo. It will be in between. This will be mixing of indigo and violet. After that, indigo blue mixing. So it is called. You see the spectrum. It is continuous spectrum. So after this explanation, is it only visible spectrum is there? No, invisible spectrum is also there. You heard about this one, the ultraviolet, infrared. If you see this video after that, where is infrared, where is ultraviolet, you don't have any more doubts. I will explain you. See this one, red. So above this one will be what is called, this one is the visible range. We can say this one is the visible range. Visible range. So this one is invisible. This one is invisible. Invisible. Clear, no? This is visible range and invisible range. So see the red one, red. So above will be infrared. Clear, no? This one is the red. See here it is red. So above will be infrared. Infrared. It is not visible. It will go up to 10,000 nanometers. So now you know red, above the red is infrared. It is invisible range up to 10,000 nanometer. Now you see the below the violet. Here is the violet. Below the violet, it is called ultraviolet. Clear, no? Why it is called ultraviolet? Below the violet, it is called ultraviolet. It is also in the, not in the visible range, invisible range. It can go up to 100 nanometers. Now everybody clear about what a continuous spectrum. It is a continuous spectrum. It is called, it is the visible range also there, invisible range also there, invisible. Above the red is called infrared up to 10,000 nanometers. Ultraviolet, it is the below the 350 up to 100 is the ultraviolet. It is invisible. Again we have learned what is a wavelength, lambda, how it is measured, how can be a wavelength, how the prism is making, glass or light, glass or water, whatever it is, the from one media to another media, the white light is going to divide into its own continuous lights like a violet, indigo, blue, green, yellow, orange, VIBGYOR. Very easy to remember. Clear? If you can take a note on this one, I'll rub it out. Can I rub? Yeah. Now we already know what is a continuous spectrum. Now we see a tube where the positive supply can be given, negative supply, and it is the Clear, no? This is a tube. It is filled with hydrogen. Okay, what is a hydrogen? Hydrogen 1, 1. It is filled with hydrogen atom. Clear, no? So, what is 1? It is the Z. What is this one? A. So, it is the atomic number, mass number. 1 is what one? Proton or electron. This one is the proton. Clear, no? Everybody, this I already explained in the previous 2 videos. If you want doubt, you can see that video. Clear. Now, if hydrogen gas is taken at less than the atmospheric pressure. What is atmospheric pressure? I am telling so many details in this video, and you can, whatever you require, you can just take it on. What is atmospheric pressure? Atmospheric pressure. Normally it is called 1 bar. It is 1 into 10 raised to 5 Newton per meter square. It is called 1 bar is equal to 1 into 10 raised to 5 Newton per meter square. Clear, no? Okay. So, I am taking this hydrogen gas inside, not in atmospheric pressure, less than the atmospheric pressure. That means less than 1 bar or 1 into 10 raised to 5 Newton per meter square, or it is called Pascal also. It is the Newton per meter square is called Pascal also. Clear, no? So, this hydrogen gas is now given with a charge. Charge means what is going to happen? The electric current is going to pass like this, from positive to negative. So, this atom inside is getting now charged. For that one, after that, there will be a radiation is emitted from here. There will be a radiation is emitted from here. Okay, we are putting a screen here. And we are observing through the camera. We just remove that one. So, this hydrogen gas now given a electric current, positive and negative. So, the charge is available now. It is producing a radiation. So, this observing that one through the spectrometer. Now, you understood what is a spectrometer. Spectrometer, there will be a prism, there will be a screen, there will be a camera. Through the spectrometer, if you see this one, you can see some discrete lines. See like this. See here, one bright light here, one bright line here, one bright line here, one bright line here, one bright line here, one bright line. Remaining all the spectrum is like a dark. This one is a dark. This one is the bright line. Bright. This one is the bright. Now you see, in the dark background, there will be a bright lights. This spectrum we are getting when hydrogen gas is ionized. So, a given radiation. Clear, no? This spectrum is called discrete spectrum. discrete spectrum or line spectrum or emission spectrum. So how many names now? Emission spectrum, discrete spectrum, line spectrum. What is meant by the name discrete? It is not a continuous one. Continuous opposite discrete, non-continuous. Line. It is called line spectrum. Emission spectrum you will understand little afterwards, because if emission is there, there will be absorption. There will be at absorption spectrum is also there. That's why this spectrum is called emission spectrum. We will just see, we will just learn little more about how this spectrum is making. Now you understood now what is that one. So hydrogen gas is there. It is getting radiated when the charge is passed through that one, and it is making some lights. So this bright lights are there. This one is bright light, this one is bright light, this one is bright light. They having a fixed wavelength for the fixed gas. This hydrogen gas, it is got a specific spectrum. For helium gas, there is another specific spectrum. So this spectrum, if you measure this discrete spectrum of a gas, is like a signature. You got a signature, you got a your thumb impression is there. That is the characteristic of this gas. Same like this is the characteristic of this hydrogen gas. We will just study here only the hydrogen gas, what is the spectrum it is making. Clear, no? If a hydrogen gas is passing through, we are getting H alpha, H beta, H gamma, H delta. Clear, no? This waves like that it is getting. So we will just write the wavelength also here. Now you see, these are the wavelength in nanometers. Clear, no? These are the H alpha, beta, gamma like that, 656.3 nanometer. You know what is the visible range? Visible range is from the 700 nanometer to 350 nanometer. So this one, you know, 700 is very near to that one. It is very near 700 range it is there. It is called, this one will be red color. Clear, no? This one you see very near to 700, that will be red color. So this will be around the blue color. Clear, no? This is red color, this one is the blue color. So this one will be around blue green. This one will be green, violet. This will be violet in color. So this is the characteristic discrete or line spectrum of this particular gas. Understood, no? How this spectrum is making by this gas we will explain little afterwards. And if I am removing this electric, now you understood what is a discrete spectrum. It is the characteristic of a particular gas when electric current is passing through it, that one, it is radiating some spectrum. It is called as discrete spectrum or emission spectrum or line spectrum. It is the characteristic. It is the only thing that gas is producing. Clear? So everybody clear what is a discrete spectrum? I am just removing. If you want, you can just write it. Please write it there. Okay, so now we studied about the emission spectrum. Now we'll study what is an absorption spectrum. Absorption spectrum. Okay. See, again I am taking hydrogen gas in a tube. Now, this time I am not passing the electric current here. I am just passing a white light. White light. When the white light passes here, this is now making some spectrum. We'll again put the screen here. Now you see this spectrum. Now the absorption spectrum we are getting here is the bright lines and here is the dark missing. Now you see this is the continuous spectrum, but whatever the emission spectrum bright lines are there, here it is missing here. It is like a dark. So now we understood what is an absorption spectrum. It is the remaining spectrum of the emission spectrum. So we can say emission spectrum, emission plus absorption is a continuous spectrum. Clear, no? Previously, the emission spectrum, there was bright background was not there, only the bright light was there. Here the absorption spectrum, bright background is there. Whatever the emission spectrum, bright lines are there, here it is missing. So we can say the emission spectrum plus absorption spectrum, it is a continuous spectrum. Now everybody clear what is a emission spectrum plus absorption spectrum for a particular gas or anything? Clear, no? So I am putting a white light through the hydrogen gas, no charging is there, then it is producing a spectrum with the white all the spectrum, but dark the emission spectrum the bright lines are missing. That is called as absorption spectrum. So emission plus absorption, it is a continuous spectrum. But we are seeing the first one, the continuous spectrum. Okay, this particular spectrum, how this emission spectrum, absorption spectrum, a hydrogen gas is making, that Rutherford cannot be explained. So we will explain how this one is making this one, hydrogen gas is making, or any atom, how it is making this spectrum. We will just learn that one. You can take this one. Okay. This is nucleus. What is it is there? It is calling a neutron is there, proton is there. Clear, no? This is a nucleus. So I am talking about the first line. It is n is equal to 1. It is again called base. Okay, this is n2. N is equal to 2. This is n is equal to 3. N is equal to 3. Clear, no? N is equal to 1. The first orbit, second orbit, third orbit. This is the nucleus. I am just writing only 3 orbits. Okay. See, this orbit, there is an, if they want to electron, here it is all rotating by electrons. Clear, no? Electrons are rotating. This first orbit, it is called base. Clear, no? It is the base one. So if an electron is revolving in the n1 state, it is the base state, then it is revolving with a electric current of minus 13.6 electron volt. If it is n is equal to 2, this is rotating with minus 3.4 electron volt. If it is the third one, it is rotating with 1.51 electron volt. If it is a fourth one is there, n is equal to 4, it is rotating with minus, this is all minus, minus 0.85 electron volt. So now you see the base one, it is required only minus 13.6 electron volt to revolve here. Here it is minus 3.4 electron volt. So tell me which one is the higher value, minus 13.6 or minus 3.4? Yeah, minus 3.4 is the higher value. So now you see this one is the higher value, this one is the higher value. So if an electron goes from higher orbit to lower the base orbit, the energy will be radiated out. This energy, it is radiating out and giving us a spectrum. Clear, no? We'll just go a little more that one. I'm just drawing here another line. So this one is the n is equal to 1. This one n is equal to 2. N is equal to 3. N is equal to 4. Okay, how much is the volt here? Minus 13.6 electron volt. Minus 13.6. Here it is minus 3.4 electron volt. Here minus 1.5 electron volt. Here 0.85 minus electron volt. If one atom is jumping from here to here, how much will be the radiation charge is produced? We will just calculate. This one jumping from here to here, it is minus 3.4 minus into minus, it is plus, is 13.6. Clear, no? So it is going to become 10.2 electron volt. So if an atom jump from second orbit to first orbit, there will be a 10.2 electron volt will be radiated. this will be coming as a line spectrum. Clear, no? If it is one electron is jumping from n3 to n1, how much will be the energy radiating outside? You can just calculate. It is a minus 1.5 minus into minus plus 13.6. It is 1.6, so 12.1 electron volt. Clear, no? So this much of electron volt energy will be produced. So this one is going to become as a radiation, or it is going to become a spectrum. Clear now how this spectrum is going to? We will go little deep on this one. We will just see how it is going. Okay, you just note it down, this one. I will go into about that one. Now you clear now? This one is the planetary method. This one is the graph method. This one is a base orbit, second orbit, third orbit, fourth orbit. The same. First one, second one, third one, fourth one. 13.6, 3.4, 1.6, 0.85. So if it is a electron is jumping from second orbit to first orbit, 13.2 electron volt will be radiated outside. If it is jumping from third to 1, 12.1 electron volt will be radiated outside. Clear now? It is, you can calculate, see this way also you can calculate. Second one, from fourth to second, third to second, you can just calculate. So third to second, how much will be there? Third to second, minus 1.5 minus into minus plus 3.4. So it is going to become 9, 3 to 1.9 electron volt. If an atom jump from N3 to N2, it is 1.9 electron volt. Some questions, some JE questions, they are asking this one. Okay, we'll do afterwards. First you can write it that one. Can I rub out? Okay, see this spectrum, there are in the visible range also, in the invisible range also. We already seen what is a visible range, what is invisible range, ultraviolet range, infrared range, everything we'll see. To calculate the wavelength, there is a equation is there. 1 by lambda is equal to R into 1 raised to n final square minus 1 initial square. Very important. You can learn like this only. Where is lambda, wavelength, lambda wavelength. Clear, no? Okay. Then it is the R, Rydberg. It is very important one. What is this R? It is called Rydberg constant. Rydberg constant. The value of the Rydberg constant is 1.097 into 10 raised to 7 meter raised to minus 1. So very important one. Rayberg constant 1.097 into 10 raised to 7 meter raised to minus 1. Now what is NF? Final orbit level, orbit number. You study like this only, because they are always telling the final one, initial one. So you study like this: NF, N1, Ni. It is initial orbit number. See, if an electron is jumping from second to 1, first orbit, so this one will be 2, this one will be 1. If it is an electron is jumping from third to second, so this one will be third, this one will be second. That way it is called the initial, this one is the final. You can learn like that only. Okay, this spectrum, there is a scientist who was called Balmer. He learned this one very early itself. 1895 itself he found that this the line spectrum. And we will just Balmer series will just write it there. Okay. In the Balmer series, always electron is going to jump only up to the second orbit. Clear, no? Electron is going to jump only the second orbit, where n initial is, if it is 2, it is going to become 3, 4, 5, etc. It is going to become, it is n initial. Clear, no? So it is going to become 3, 4, 5. We will just do one calculation how this spectrum is going to come. We will do a calculation. Can I remove this one? Okay. Okay, now I am going to write a electron jumping from third to second. Third to second it is going to jump. An electron is jumping from third orbit to second orbit. Okay, I am just calculating 1 by lambda is equal to 1.097 into 10 raised to 7 into 1 by 4 minus 1 by 9. Clear, no? So it is become 1.097 into 10 raised to 7 into 5 by 36. Clear, no? You can just calculate. So now I am just calculating lambda is equal to 36 divided by 5 into 1.097 into 10 raised to 7. Okay, I am just calculating. If you divide this one, it is going to become 6.563 into 10 raised to minus 7 meter raised to minus 1. Okay, you see this one. Now I am going to multiply 2 more. So is equal to 656.3 into 10 raised to minus 9 meters. Okay, this is how much? This is a nanometer. I am just removing this one. 10 raised to minus 9 I am removing. It is a nanometer. Now you see the visible spectrum was started. Now I'll just draw the visible spectrum. You see the visible spectrum. H alpha. H alpha, how much was the wavelength? 656.3 nanometer. So, an electron jumping from third to second. So, it is coming in the visible range. So, we'll just write one more from 4 to second. Now, third to second, 4 to second, again in the Balmer series. So, I am just calculating again. 1 by lambda is equal to 1.07 into 10 raised to 7 into 1 by 4 minus 1 by 16. Clear, no? So, I am just writing, this one is 2 square, this one is 4 square. Clear, no? So, I am just going 2 square, Ni is 4 square. So, it is going to become, it is 1.097 into 10 raised to 7 into 16 minus 4 divided by 16 into 4. So, 16 minus 4 is 12. So, lambda is equal to 16 into 4. 16 into 4 how much? 16 into 4. 64. 64 divided by 12 into 1 by 1.097 into 10 raised to 7. Okay, this is going to come how much? 4.861 into 10 raised to minus 7 meters. Now you see, I am calculating again. It is going to become 486.1 into 10 raised to minus 9 nanometers meters. So, I am 10 raised to minus 9 meters. 486 into 10 raised to minus 9 meters. I am converting 10 raised to minus 9 meter is nanometer. I am just taking out this one, 481 nanometer. Now you see, it is jumping from 3 to 2, we are getting the first spectrum. When it is 4 to 2, it is getting the spectrum visible second one. So, if it is jumping from, now you see 4 to 2, 5 to 2, you will get the third one. It is how much that one? 434.1. So, we can say it is the 3 to 2, it is jumping. It is 4 to 2, it is jumping. It is 5 to 2, it is 6 to 2. H delta. Clear, no? Yeah. Yeah. So, an electron, it is jumping to second orbit. Now you see the second orbit, 4 to second orbit, 5 to second orbit, 6 to second orbit. You will get the visible range of Balmer series spectrum. So, in the energy level calculation we will see, this is what we want to learn it now. Any electron jumping to second orbit, we will get the line spectrum in the visible range. That is what we want to learn it now. Is it an electron can only jump to second orbit? No, it can jump to first orbit also. It can jump to third orbit also. It can jump to fourth orbit also. But if an electron jump to second orbit, you will get a visible spectrum. That is what I just want to say. So can I remove this one? Clear, no? If it is jumping from, this one is 1 by lambda. Lambda is the wavelength. R is Rayburg constant. How much is the 1.09 10 raised to 7 meter raised to -1? That is a Rayburg constant. N final, N initial square. So how we are doing the calculation? This is coming in the visible spectrum. Visible spectrum. Clear, no? So you can just write it there. I'll rub it. I'll just write the equation. 1 by lambda is equal to R into 1 by n raised to final square minus 1 by raised to initial square. If it is a Balmer series, a visible range, the equation become 1 by lambda is equal to R into 1 by 2 square minus Ni square, where Ni is equal to 3, 4, 5, etc. Understood? Now, if it is jumping from third orbit to second orbit, then only the energy will go out. Then only the radiation will be there. Then only the spectrum will be seen, that one. For that one, you need an excitation. You see that previously the electric current was passing through, then it is getting excited, then the radiation will start. At that time, what is happening was, when an electron jumping from third orbit to second orbit, or fourth orbit to second orbit, fifth orbit to second orbit, that way the visible range was producing. That only the Balmer was seen when 1985 he invented this Balmer series range, 1985. Before the Rutherford found out the atom model, nuclear model. Before itself he found out the Balmer series visible range. Clear, no? So it is very important, that one. They are going to ask so many questions regarding that one. We also will be doing that one. So Ni is 3, 4, 5. So it is in the visible range. So is it only the visible range spectra is making when atom is getting excited? No. It is going in the ultraviolet also. It is going in the infrared also. Everybody clear what is ultraviolet, what is infrared? Clear, no? Okay. So next one is Lyman series. Everybody clear now how it is coming, the 2 here? The same way, Lyman series 1 by lambda is equal to R into 1 by 1 raised to square minus 1 Ni raised to square. Can you tell what is the value of Ni here? Ni will be 2, 3, 4. Like that will continue. See, the same way, if an electron jump from second orbit to first orbit, the Lyman series of spectrum will be making that one. Is it visible? No, it is in the invisible. Which range it is? It is below ultraviolet range. Clear no? How it is the Lyman series is making. So it is 1 by lambda r. It is jumping from second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit. Clear no? Okay. Now second one is Paschen series. One by lambda is equal to r into 1 by 3 square minus 1 by ni raised to square, where ni is equal to 3. So it is go 4, 5, 6, etc. Now you see this one. If an electron jump from fourth orbit to third orbit, it is going to become Paschen series. Is it visible? No, it is not a visible. It is a invisible. It is in the ultraviolet? No, infrared region. Clear, no? Okay. Paschen series. Next one is Brackett series. Brackett series. Okay, this is jumping to the fourth spectrum, fourth orbit. So Ni will be 5, 6, 7. Like that will go. Is it visible? No, it is again invisible. Invisible infrared range. Clear, no? Okay. Next one is, we can say Pfunesd. It is very simple. After Pfunesd, what is that? 1 by lambda r into 1 raised to 5 square by ni square, where ni is equal to, it is not a 5, it is 6, 7, 8, 9. It is also invisible in the infrared above region. Can you just calculate the wavelength of this one here? We'll just calculate here. Can you calculate the Lyman series on wavelength? We'll just do here itself. You can just see there. 1 by lambda is equal to 1.097 into 10 raised to 7 into 1 minus, I'm just taking second one, 1 by 4. Okay. So lambda is equal to 4 minus 1, 3. So 3 by 1 by lambda. 1 by lambda is equal to 3 by 4. 4 into 1.07 into 10 raised to 7. So lambda is equal to 4 by 3 into 1 raised to 1.07 into 10 raised to minus 7. This is 7. Okay. So this is going to become 3 by 4. It is going to become, how much is going to be? You can just calculate and see. It is going to become something like a 103 nanometers. So it is going to become 103 or something nanometer. It is in the, we can see the below the 360. Below the 360 means it is in the ultraviolet range. So you can just calculate this one. Very simple calculation. This is going to come sometimes in the JEE main exams. Very simple. Very simple. So you can just note it down. I'll rub it out. Okay, so today what we have all learned? We have learned what is a continuous spectrum. What we have learned is a discrete spectrum. That is also emission spectrum, absorption spectrum. Then Lyman series. It is jumping from any orbit to first orbit. It is the Lyman series. If it is jumping to second orbit, it is the Balmer series. It is visible range. Then it is the Paschen series. It is jumping to third. Then it is coming to the Brackett series. Then it is the Pfunesd series. Everybody learned this one. We will do some NEET question and or JE questions here. It is very important one. Mostly all these questions are beating in different ways. Okay. Okay, we'll just read the question. Whenever a hydrogen atom emits a photon in the Balmer series. So this is the NEET question answer. You can just, whenever hydrogen atom emits a photon in the Balmer series, it need not emit any more photons. It may emit another photon in the Paschen series. It must emit another photon in the Lyman series. It may emit another photon in the Balmer series. So, to understand this one, we need to know what is a hydrogen atom. Hydrogen atom, how many photons are there? Hydrogen atom, I will just draw that one. Nucleus, one electron is there. This one is the n is equal to 1. Clear, no? This is electron 1 at the 1. Whenever a hydrogen atom emits a photon in the Balmer series, Balmer series means how much? It is n is equal to 1 by lambda is equal to r into 1 by second square minus 1 by ni square. So, Balmer series means the electron is now in the second orbit. So, electron is now in the second orbit. Normally, the hydrogen atom is, electron is in the base orbit, the ground orbit. It is in the first orbit. So, it cannot stay there. So, it must come to the first orbit. Everybody clear now? If it is in the Balmer series, the electron is in the second series now, second orbit. So, to get in the stable state, that electron should come back to the first orbit. So, to come to the first orbit, what is there? It need to emit one more electron from the, now this electron is in the second orbit, n is equal to 2. To come to the stable, it come back to the first orbit. So if it is coming from second orbit to first orbit, it is what is called Lyman series. So answer is, it must emit another photon in the Lyman series. Very interesting, very easy question, no? I'll just explain once again. A hydrogen atom emit a photon in the Balmer series. So hydrogen atoms emit in the Balmer series. Now the hydrogen atom electron is in the N2 state, because Balmer we know the final state will be N2, second state. So the hydrogen atom will not be stable if the electron is in the second state, because the electron should come in the first orbit. To come to second orbit to first orbit, it should emit a photon in the Lyman series. Clear, no? Very easy question. It is answer is, it must emit another photon in the Lyman series. Very simple. You can knock it down. Like that, if you know the things, it is very simple questions. Violet to red. When a white light, violet to red, is passed through hydrogen gas at room temperature. Absorption line will be observed in the, this is the question. When a white light, violet to red, that means visible light, is passed through hydrogen gas at a room temperature, absorption light will be observed in the answer. Lyman series, Lyman and Balmer series, Balmer and Paschen series, okay, I'll just read the question once again. When a white light, violet to red, because they are telling violet to red because it is a visible light, visible range. That's why you want to take white light. They want to tell it is the visible light. That means there is no much power. It is not a no. It is a normal light. It is passing there. Is passed through hydrogen gas. You remember the hydrogen gas I told you? It is hydrogen gas is passing at room temperature. Very important. Room temperature and white light. These two are things are very important. Room temperature, absorption light will be observed in the, you know that one, absorption light, emission light will not be there, absorption light will be there. But in this two things are there. The white light is passing at a room temperature. Normally you see there will be a, you see that one, in absorption spectrum there will be a electron volt required to jump from 10.1, I told you that when 10.1 electron volt is required for jump from this state to this state. That 10.1 electron volt is not available with white light in the room temperature. Very clear, no? This 10.1 electron volt hydrogen atom. It is hydrogen atom at a hydrogen atom. So it is a 1. It is the n is equal to 1. So from second to 1. So or 1 to second. So it is going to 1 to second orbit. It is going to jump out. So 10.1 electron volt is required. For a white light, room temperature, 10.1 electron volt is not available on the light. So Lyman series is not there. Lyman and Balmer series is not there. Balmer and Paschen series is not there. Answer is absorption line will not be observed. Absorption line will not be observed. This one is the correct answer. Clear, no? Because 10.1 electron volt is not available in that light of white within the room temperature. Hi friends, clear? So we learned very complicated. I think this one is very complicated in the atom, but we are explained very easily. We have learned today what is a continuous spectrum, discrete spectrum, line spectrum, then we are emission spectrum, absorption spectrum, Balmer series, Lyman series, Paschen series, everything we have learned that one. Then we did some NEET question answer, JE question answer. Happy? So learn well. If you got any doubt, you can put it in the comment box. I will clear you. Thank you very much. Thank you. Bye. See you next time.